Particles and antiparticles. Antiparticles are an example of antimatter, and all particles have a corresponding antiparticle. The electron antineutrino emitted in beta minus decay is an example of an antiparticle. When a particle and its antiparticle meet, they annihilate each other, converting their mass into electromagnetic radiation. So here we have a particle and an antiparticle. When they meet, they emit two photons of electromagnetic radiation travelling in opposite directions. And when the two meet, they will emit two photons, both going in opposite directions. The two photons have to travel in opposite directions to ensure that momentum, which was zero initially, will be zero afterwards. Momentum has to be conserved. A photon can also change into a particle-antiparticle pair. So here we have a high-energy photon, which will split into a particle and an antiparticle. Antimatter, annihilation between particles and antiparticles, and pair production all build from Einstein's famous equation E equals mc squared, although you're not expected to do calculations involving this equation. This shows that mass is a form of energy. The E is energy, the m is mass, c is just the speed of light in a vacuum. This means that mass can become photons and vice versa. Antimatter was predicted by Paul Dirac back in 1928. It was 4 years later that the first evidence of an antiparticle was seen, and this was an anti-electron, which became known as a positron. I'm just going to look now at positron emission, which can also be called beta plus decay. Positron emitters don't occur naturally, but we can make a nucleus with surplus protons artificially by bombarding stable isotopes with protons, and some of these protons get captured by nuclei. In beta plus decay, a proton becomes a neutron, and in so doing emits a positron and an electron neutrino. You might recall that in beta minus decay, a neutron becomes a proton, kicking out an electron and also an electron anti-neutrino. Here we have the general equation of beta plus decay. So we have one nucleus which I'll call X, and this is Z, its atomic number or number of protons, A, its mass number or number of nucleons, protons and neutrons. Now a proton becomes a neutron, so we go down to 1 lower, or Z minus 1. But the mass stays the same. A proton weighs the same as a neutron, so A stays the same. We get a new isotope, Y. This will be a new element, as it's lost a proton. We also get a beta plus particle, which has a mass of 0, but an atomic number of +1. It has to balance the equation. So here we've got Z must equal Z minus 1 plus 1. We also get an electron neutrino. Antiparticles have the same mass as their particle, but the opposite charge. In annihilation, a particle and an antiparticle produce two photons. The energy of the photons has come from the mass of the particle and the antiparticle. The energy of the particles will be given in mega electron volts, where a mega electron volt is 1.6 times 10 to the minus 13 joules. The energy of a photon is given by hf, where h is Planck's constant, 6.63 times 10 to the minus 34 joule seconds, and f, the frequency of the photon in hertz. If the annihilating particles also have kinetic energy, the photons produced will have more energy. If the particles produced in pair production have kinetic energy, this must have come from the photon. So, in annihilation, if we take E0 as the rest energy of the particle, this must be in joules, though it will be often given in mega electron volts. H, as usual, is Planck's constant, and f min the minimum frequency of one of the photons emitted. We can say that 2 times the rest energy of one of the particles, as we have a particle-antiparticle pair. Particles and antiparticles have the same mass, and so will have the same rest energy. This will be equal to 2 photon energies, the photon energy being given by Planck's constant multiplied by the frequency. This is because 2 particles produce 2 photons. So we have the rest energy of 2 particles producing 2 photons. However, as the particles and the photons will have the same energy, we can simplify to the rest energy of one particle will equal the energy of one of the photons. In pair production, we can say that 2 times the rest energy of a particle will equal the energy of the photon, because in this case one photon produces 2 particles, so we have the energy of 2 particles coming from the energy of one photon. This table lists some particles and their antiparticles. First we have the electron, which can be given the symbol of a lowercase e with a minus sign, or the beta sign with a minus sign. Its antiparticle has a special name of positron, and this can have the symbol of an e with a plus sign, or beta with a plus sign. The beta part comes as this is a beta plus particle, this is a beta minus particle, but you may see both notations. The proton, symbol lowercase p, and the antiproton, same symbol but with a line over the top. Likewise for the neutron, lowercase n, the antineutron, lowercase n with a line over the top. Neutrinos all have this symbol, but have a subscript e for the electron neutrino, a subscript mu for the mu neutrino, and a subscript tor for the tor neutrino. The symbols are the same but with a line over the top for the antineutrinos. Like I said before, particles and antiparticles have the same mass but opposite charge. Now I'm just going to run through a couple of examples. An electron has a rest energy of 0.512 megaelectron volts, or MeV. Part A. What is its rest energy in joules? Well, to go from electron volts to joules, we multiply by the charge on the electron, 1.6 times 10 to the minus 19 coulombs. And so in this case, we have 0.512 times 10 to the 6 electron volts as its mega electron volts, multiplied by the charge on the electron, gives us a rest energy of 8.19 times 10 to the minus 14 joules. Part B. Calculate the minimum frequency of photons emitted if it meets and annihilates a positron. Well, we know that the rest energy of the electron is equal to Planck's constant multiplied by the minimum frequency of the photon emitted. So we can rearrange that the minimum frequency is equal to the rest energy of an electron divided by Planck's constant. The rest energy of the electron has to be in joules, which is what we found here. Planck's constant from the data sheet, 6.63 times 10 to the minus 34 joule seconds, giving a minimum frequency of 1.24 times 10 to the 20 Hertz. Part C. Why must the annihilation create 2 photons? Well, it must conserve momentum, and as the photons go in opposite directions, if each has the same magnitude of momentum, momentum will be 0 before and after. Next example. Calculate whether a photon of frequency 5 times 10 to the 23 Hertz can produce a proton-antiproton pair, and it gives us the proton rest energy of 941 mega electron volts. Well, in this case, 2 particles are produced, with E0 being their rest energy, from 1 photon of energy Planck's constant multiplied by the frequency. We want to find the frequency, which will be given by twice the rest energy over Planck's constant, and putting the numbers in, we have 2 times 941 the 10 to the 6 because it's mega electron volts, multiplied by the charge on the electron to get the energy into joules, divided by Planck's constant, giving a minimum frequency of 4.54 times 10 to the 23 Hertz. As the photon we have has a greater frequency than this, we can say that the photon could produce a proton-antiproton pair with kinetic energy. The particles will be moving after the pair production.